All right. Good morning, class. Hope everyone's doing well. Um, I'll tell you what, I slept in a whole lot, and I woke up at about 10 o'clock this morning, and I think I slept for like 13 or 14 hours last night, so I feel pretty groggy. So I'm drinking some coffee. This is my coffee mug. You can see it's got a brown Boston Terrier on one side, and it's got a black Boston Terrier on the other. So it's a perfect coffee mug for me. The other thing I wanted to say is try to support local businesses if you can. Last night I got some takeout from my favorite Indian food restaurant. It's called Ashirwad, and if we don't buy food from some of these places, they might go out of business. So support your favorite restaurants. Get some takeout if you can. Thank you, Camille. I agree. It is a cute coffee mug. All right, I think I'm back. What we're going to talk about for the next 2 days is what happens if you have a circuit that looks like this. So this is a circuit that consists of a battery and no resistor. Okay? So we have a battery and no resistor. So if you were to just naively apply Ohm's law to calculate the current that flows, we would say I equals V over R. Thank you for your patience. We would notice that current is V over R. So if there's no resistor in the circuit, then that means that R equals 0. So we get V over 0 equals infinity. Infinity amps. Oh my gosh. That's crazy. What's going on here? Well, there's actually two issues with this calculation. The first issue, which is the one that we're going to talk about tomorrow, is the first issue for tomorrow is that batteries aren't perfect. The first issue is that so wires are not perfect. Okay. Let me try it. I'm going to close this. Maybe that'll make it a little bit easier to read my writing here. Okay, so this is what we're focusing on today. So let's consider a wire. So what does a wire look like? Well, here's a section of wire. So maybe the wire looks like this. So the wire has a certain cross-sectional area, which I'll denote by A. Okay. And depending on the geometry of the wire, it could be a number of different things. If it was a circular cross-section wire, it's going to be pi r squared. If it's a rectangular wire, it's going to be length times width. You know what I mean, etc. If it's a triangular wire, the cross-section is going to be 1/2 base height. I don't know if there are any triangular wires out there. Maybe there are, maybe there aren't. Okay, so that's the area. L is the length of the wire. Okay, so the geometry of the wire determines its resistance. Okay, and then the other thing that determines the resistance of the wire is the material. Is the material a good conductor? Is it a bad conductor? Is it an insulator? Okay. So these are the things that matter. So there's a nice formula for the resistance of the wire, and it is rho L over A. So this is our equation for today, rho L over A. Wow, that's a really good rectangle I drew. Look at how perfectly that closed up. Amazing. What L is the length of wire. So you see how L is in the numerator. So that means if you have a really long wire, the longer the wire is, the more resistance that wire is going to have. So if you have super duper long wire, for example, the wires that are used to carry power from the electrical station, from the place where the power is generated to your house, that's a long wire because you don't have a power station in your neighborhood. That's going to have a pretty significant resistance. So basically, resistance increases the longer the journey is. That makes perfect sense. We can see area is in the denominator. Okay. And area, the bigger the area is, basically the fatter the wire is. Okay. Again, this is sort of like adding more lanes on a freeway. Okay. The more lanes you have, the more routes there are for charge to get from point A to point B. And so that decreases the resistance. Okay. Bigger area decreases the resistance. Longer wire increases the resistance. So what is this? This is the Greek letter rho. And rho is called the resistivity. Okay, so it's not the resistance, it's the resistivity. And the resistivity is a property of the material. It's a property of the material. Okay? So basically L and A, that's where the geometry comes into play. And rho which is the resistivity, is where the actual what it is made out of comes into play. The units of resistivity are ohm meters. All right? So let's do an example with resistivity. Okay? Let's suppose we have a triangular wire is made of of copper, a triangular wire is made of copper. It is, or I should say it is, okay, let's say it is 1 mile long. It has base, let's say the base is 4 millimeters, and the height is 5 millimeters. What is the resistance of the wire? Okay. So first of all, I better look up what is the resistivity of copper. So you would never have to memorize this. You would just look it up. Okay. And so I'm going to change the scene. And I'm going to look up resistivity of materials. Okay. And oh, look at that. First result, table of resistivity. And so if we go here, we can see copper is right here. And it says the resistivity is 1.68 times 10 to the minus 8 ohm meters. So let me write that down before I switch back. All right. So the resistivity of copper is 1.68 times 10 to the minus 8 ohm meters. Now it is possible to kind of predict what it is, what the resistivity is going to be but you could only do that at a much more advanced level. Okay. So for this class, you just look it up. Good conductors have a smaller resistivity. Okay. As far as the area is concerned, the area, it's a triangular wire, so the area would be 1/2 base height, which is going to be 1/2 times base, which is 4 times 10 to the minus 3, because that's millimeters, so millimeters means times 10 to the minus 3. And the height is 5 millimeters. Okay, so 5 times 10 to the minus 3 is the height. So, looks like this gives us 10 to the minus 5 square meters is the area. And then the length is 1 mile. We better convert that to metric. And I happen to know, since I like to run, that 1 mile is 1,609 meters. Okay, so then we go down here and we calculate the resistance. It's rho, 1.68 times 10 to the minus 8, L, 1,609 over A, 10 to the minus 5. So that many ohms. I'm just gonna ballpark it here. I'm just gonna approximate it. Okay. Just for fun, I'm gonna treat 1.68 times 10 to the minus 8. That's approximately 10 to the minus 8. 1,609. That's approximately 1,000. 10 to the third. And then 10 to the minus 5 on the denominator. So if you work this out, this is approximately 1 ohm. So this wire would have a resistance of approximately 1 ohm. Just to put that in perspective, so you guys are kind of missing the experimental component of circuits, which is a bummer because it's really fun. But 1 ohm is not very much resistance. Okay, a typical value for an actual resistor is usually about 1 kilo ohm, which is 1,000 ohms. All right, so 1 ohm is not very much at all, which is why most of the time we can actually neglect the resistance of the wire. But if the wire is the only resistance present, such as right here, it can become a significant factor. So when you would need to include the resistance of the wire in your calculations is if the actual resistors in the circuit are very, very tiny. All right. So that's my lesson for today. I hope you're all doing well, and I hope to hear from you. I hope some of you guys will join us in the Discord discussion, because I would love to hear your voice or have a instant message conversation or something like that. All right. So have a nice day. Bye.